Hello community! Today we talk about CodeLLMs and we explain everything about it. So if today, Monday 11th November, I go here Hugging Face and I have a look at the code, we have more than 12,000 code models, which are just great. Every minute there's a new code model. However, if we sort here for trending, you see just one day ago from Cuban, our Chinese friend, 2.5 coder, 7B instruct, and it has already been downloaded 73,000 times. One day ago. So there's a massive interest here in CodeLLMs. If you compare this here with DeepSeek Coder here from July, you see starting from July to November, it just downloaded 100,000 times. So are those open source so much better? Let's have a look. So here we are in Hugging Face. We click on this Q1 2.5 coder 7B instruct. We have all the information there is, but what's really interesting, always check the license. Apache 2, open source, great. So if you want to run this and have an operational CodeLLM, they give you here the complete Python code. You just take this here on the page, string copy, put it in your Python environment, execute it. You have here the model name. You have here your prompt, whatever is your task here, for example, write a quick sort algorithm for whatever. Maybe you specify that you're operating in Python and it's normally in an English language. Great. And then you get the code. So this is it, there is, and since it's a 7B model, you could theoretically even download it locally, or you go for security reasons, maybe cloud-based. So you have an open source operational CodeLLM. Now you might ask, but how good is it? Well, there's a community voting. So you go to lmarena.ai, you go here in coding, and then you look at it. But unfortunately, since it was published yesterday, it needs 3, 4, 5 days sometimes that a community vote accumulate, and then we will have it. So if you see this in 1, 2, 3 days, maybe you already see it. If not, we have here the old Q1 2.5, the 72B, the more or less non-code optimized version here at position at rank number 6. And you see here, top ranks, of course, all our friends that we know from OpenAI, from Claude Sonnet, from Gemini, from Grok. And then we have here on rank number 5, the Meta Llama 405 billion free trainable parameters. So you get a good idea, proprietary CodeLLMs and open source CodeLLMs. And then I got a lot of questions from you and say, hey, explain why some CodeLLMs are better than others. And then you ask me, hey, should I go and pay for Copilot Plus or this new Windows intelligence? You know, since Apple had this Apple intelligence, now Microsoft is going for the Windows intelligence marketing slogan. Or Cursor, should you pay Cursor? Should you pay Bolt? Or should you build your own CodeLLM if you only have a small company with a narrow domain? Maybe you work only in the English language and you have only a Python or a TensorFlow environment. And then all your questions, hey, should I go with those proprietary black boxes where I have no idea how to do the code, or should I build your own? And you ask, hey, what are the latest technology to build your own? And we're gonna answer everything today. So, how do they work? Explain CodeLLM. Okay, here we go. Human. I start with a plain English sentence and say, hey, you stupid machine, write a Python code that fine-tunes here a sentence transformer on new scientific publications. This is my human part. Now, the CodeLLM is normally an LLM, as you would guess. In the pre-training additional, it was exposed here to, let's see, the Python code of, let's say, simply 1 million GitHub code repos. And you know you always have the exactly what the code is all about, and. Now, the next step is we embed here all this code in a high-dimensional vector space. Sometimes it's also called a feature space. Yes, it is almost the same. People ask me, but how is it possible if I have code that I come to a vector? Well, it is easy. A simple example. Let's say this is already here, the first position of a vector, this is the second position of a vector, and the third. So first we say, what is the human language? We go with English. English, if we're in China, might be number 17, so the first vector component is 17. The second vector component is then the computer language. Let's see, Python. maybe in US it's number 1. So 17, comma, 1, comma. Next one is what you want to do. Here, for example, I want to fine-tune something. Fine-tune is in the vector space category 128. 128, my third component. Fourth component. What is the object? A sentence transformer. So sentence transformer is 58. So in this very simple example, you see it's so easy to build up here, and you get subspaces and another more detailed subspace in this space. So you have here the very simplified mathematical vector space construction. Of course, in reality, it is much more complicated. We go here only with a 1024 dimensional vector space, not 10,000 dimensions in a vector calculations. So we have compression and optimization and everything, but just to give you a very first idea. So all the code is now here in a vector space, in a feature space. And now it is easy. You know this from LLMs, no? I have here my query. And now here, just this query is transformed now here in a vector representation. This is now my embedded vector in this particular vector space that was constructed on this 1 million GitHub repos in the pre-training phase. So I have here my vector representation of this human sentence. And then let's say here, this is here the code snippet that is exactly the answer to my query. Now you can imagine if I have 1 million repos, let's make it easy, we have 1 million vectors, and you know now what's going to happen. Somehow we have to figure out, if this is the query, how we can optimize the query, that the vector of the query now starts to go here really towards our solution. So we have a prompt embedding. Now the system is trying to have here construct here a more precise prompt, check out the embeddings, explore here the code space, the code vector space, and this is all there is to it. So what we just want, if we calculate then, for example, in this simplest case, a cosine similarity between my prompt here, my query, and the answer, that this here then, this code element here, is really the closest by code element here. And then I have here detected my answer. And this is how a CodeLLM works. That's it. Now, there's a little bit of a problem, because you can imagine if we have 1 million vectors somewhere, and each little code element, code snippet that we have here, they are here distributed all over our space. And let's say we only have a 2-dimensional space, and here we have some of those code snippets now. So if you now want to test it out, if you want to move to the answer, you have to test these little code snippets out. So this is our next step. We call it a unit tests. This is simply a validation mechanism to determine if a code snippet here, this one or this one or this one, correctly performs the task that I have here in my prompt. And is it able to solve it 100%? Yes, check, perfect, we have a solution. It is that simple. If you wanted to make it a little bit more professional, I have here the latest research paper we're also going to talk about. What is the latest technology we can use here? And you have here also the code space. What I have here in this beautiful dark color, we have now here in the yellow. And you see here with a code space optimization problem. And we start here at this particular point. And now you question yourself, okay, so where should I go? No? What is the best solution? And you have here color-coded here, 0 tests passed is the bright yellow one. Then 1 of my unit tests passed. If I go here and say, oh yeah, this is successful. This is this light green area. Then if I say, hey, the next one also, I passed this one. I have then the middle green area. And I say, hey, yeah, passed. Yeah, this is the right direction to go. These are my 3 tests passed here, the dark green area. So you know exactly more or less, if you want here, if you have a gradient calculation, where we should go. But we're not going to do this with a gradient. We use a new methodology. So what we have established is a best of n methodology, where you simply dot it. No, you just try it out. You start here, you start here, you start here with your prompt. You modify your prompt at suddenly here. And then you look at it and say, hey, now this is a nice one. No? This is the start, this is the solution. So you just dot it here like a blind dart. You just throw here vectors into your vector space, And you say, okay, if something sticks and if it's a good calculation, this is the solution. Or you do a line search. This is the second methodology. You start somewhere and then you say, oh, just go here in a particular direction. 1, 2, 3. Okay. And then some touching here, this light green, I say, oh, that's it. Perfect. I have found my perfect solution. Or more advanced, you have a tree search. So you start here and you say, I don't go in one direction, but I diverse like a tree structure with my branches now. I built here a subnode, and from this subnode here I have minimum 2, 3, or maybe 6 further sub-branches. And then you start to explore here the local environment and this vector space. And you see the darker green it is, the more tests are passed. So maybe this is the direction to go. So you see, they decided here to go for this one. So these are established methodology, best of n, line search, and tree search. And now let's come to the solution. This new methodology uses now a combination of scattering, foresting, and scouting. Sounds amazing, but as you can see, I've chosen this visualization because it's very easy to understand here in these images. Scattering encourages our tree search to explore more diverse solution. So you start here, and then you say, okay, I go here. No, maybe I go here. I just scatter around here in my local environment, and from here I go there, or there, maybe there, and then over there. So you see kind of an irregular path. Foresting is a little bit different. This boosts here more the exploration by performing here tree search dynamically from multiple random seed solutions. So like throwing the darts here into our vector space, we say, okay, I start here, I start here, and I start here. But I don't just make a unit test and say this is the solution, but I move around from here. So this is just my starting point. So I go here and here and here and here. And then you see if I do this, then this dart here. Yeah, if I go here and here, here's the perfect solution. I'm coming closer here to my minimum. And scouting here shares here a successful routing. This is that we have now a feedback of our scouts exploring here this vector space. And if you see, they are here coming down and say, yeah, in this direction, this is successful. And this is feedback here, the complete tree structure. Now here this, let's say little node, little branch here says, okay, if they tell me here we should go here northeast, so I also try to go northeast, and yeah, I found here my dark green area. So here we have, if you want, a communication protocol established. Hey, here in this direction it looks interesting, so success attracts success. This is it. This is the new methodology. If you want to implement this yourself, this is the main idea of the latest technology for CodeLLM optimization in the code space that is a vector space or a feature space. And normally we go around 768 to 1024 dimensional vector spaces. That's it. Yeah, the name, of course, sorry, new methodology needs a new name, scattered forest search, yeah, for how LLMs generate code, the very latest. And the key idea here is to explore the code solution space much more effectively. Perfect. This is the study we are talking about, Rensselaer Polytechnic Institute, Princeton University, NEC Laboratories. It was done at an internship at NEC. Real nice. So the main three techniques, scattering, foresting, and scouting. Of course, I've given you now the idea, and you know we have to code this, so we have to have a mathematical implementation. And yes, of course, you know from our videos, we have here a Monte Carlo tree search, and we will utilize here the UCT formula in a particular way. And if you look at this, you might say, maybe I'm not familiar with this. Can you help me and provide some literature? Of course. I've here from the library, because this is not available online. Can you imagine this here? From March 2012, Survey of Monte Carlo Tree Search Methodologies. So here you have everything that you need. Our UCB, our upper confidence bound here. On page 7 here, you have it the first time, UCT algorithm. Here the pseudocode for the UCT algorithm. And then I found even from ResearchGate here a link that you can even read it. But I don't know if this is an official link, but the link is working if you want to read this in the official 2012 publication. Otherwise, we go back here to our very latest publication, and also for the proposed techniques of scattering and foresting. They also do this here via Markov chain theory, and they go here with diverse transition kernels, with conductance and mixing times. And they apply the formula that we need. And here it is much easier for me because there's here a beautiful online documentation. A lot of sources. I personally would recommend you here Markov chains and mixing times here from those authors, University of Oregon, Microsoft Research, and Oberlin College. And the beauty is you have here in this PDF 461 pages. So I think if you have any question at all about Markov chain and mixing timing here and all the formula that you find here, this is, I would call it a book already. This is really, maybe you would like to download here this PDF. So whenever you have some questions about Markov chains, this is a real nice reference. Of course, we can now formulate, having now this knowledge and having read all of this, in a little bit more mathematical version if you want to code this. So let's have again a look at our three methodologies. The first one is scattering. So directional diversity in branching out on our tree structure. This is scattering uses an adaptive Markov chain transition kernel, which samples here diverse improvement directions before generating the new solution. It increases here the spectral gap and the chain's conductance, enhancing the likelihood of transitioning between distinct regions in the feature space and avoid our local optima or minima, whatever we have, so we're not trapped into a local solution. Foresting, second option here, introduces here a multi-start optimization approach. Remember, these are our darts that we throw here just in our high-dimensional vector space, where a set of seed solution initiates here the search from distinct points across the complete feature space. And we use here the upper confidence bound within the Monte Carlo tree search framework to prioritize our seed evolution dynamically. And last one, scouting, maybe the most interesting one, because we have here an active feedback algorithm in our tree. Cross-branch feedback propagation here, inspired by swarm intelligence, and you might smile, yeah, absolutely. Scouting transfer here validated feedback from one branch to inform other branches, guiding here the solution evolution much more effectively. So if one branch identifies a promising solution vector, this success is shared globally in the complete tree structure. And scouting utilizes here the Q-value backpropagation along each search path to update here the UCT-based evaluation functions. Great. If you want to see my video on swarm intelligence, it is a very, I would say short, no, but it's almost an hour video here where I explain swarm intelligence, maybe a little bit more on a multi-agent ecosystem, but with hardly any mathematics at all. The result. What are the benchmark data? What is the performance of this beautiful new system? Now here you have different tests, different benchmark methodologies, and you see here, as I told you here, the best of n, or align, or the Bayes, or Monte Carlo tree search itself. And yeah, you judge yourself. So 53 with Bayes 58 with the Monte Carlo tree search, you're almost at 60. If you go just with best of n, you just throw darts in the dark of your vector space, you can achieve 65%, and with this you can achieve 67%. So whatever you make out of this, a very interesting new methodology, a new technology. But maybe if you say coding is a little bit tough on the mathematical side, maybe you just go here for the best of n methodology. It's real simple to implement. So what is the plus side? What we have here? We have here, as you know, as always, when we work here with Monte Carlo tree search, exploration versus exploitation, our sensitive balance. And here our new methodology, SFS, promotes here the exploration through the scattering and the initial seed diversity, while the third methodology, the scouting, helps with the exploitation phase. It is computational efficient by avoiding here repetitive cycles in local minima. It reduces here the computational cost and enhances the solution discovery speed. So really nice. What is the negative part? Could be theoretically a negative part here. You are really dependent here on the validation feedback quality. especially do have the validation tests here. If you use, this is done by another CodeLLM, if you use here a system that is not really up to the task and the validation task, they are so sensitive. If you make a mistake here, the whole system could collapse. Also, the complexity in the branch management. If you have really a complex, huge tree with multiple branches, remember maybe we're working in 1,000 dimension, you have here maybe a problem here with integrating all the feedback and here global communication. This could introduce some computational overhead, but I'm sure there's a new mathematical optimization methodology that has not just been found or implemented yet. So there we have it now. This new insight here of this brand new research here is now here for optimizing code generation task by our CodeLLMs. So this is the way to find here a better code for your query. Don't have to explain this to you again. This is the study. If you want, it's a very nice read. They explain much more in detail. They give you much more evaluation data. They give you much more performance data. So if you want to have a deep dive, I think this is it. But the main idea, the main performance features, and the main methodologies we went through in this particular video. So therefore, here you have it. I hope you enjoyed it. This is all about coding LLM in a nutshell. Why not go, and if you have only a narrow domain that you're working in and you want to build your own code LLM, it is not really a problem at all. If you say no, there are some beautiful open source code LLMs available. You don't have to pay anything. And I think in the next month we will see a lot of new code LLMs coming out. So maybe also explore here a cost-free option for the code LLM. But if you insist, or you work in a company where the company pays you here the Microsoft Copilot or whatever, or you go with Cursor or any other commercial implementation, test it out. Maybe you have here a 1-day free period to test it out. And after the testing, then I think you will find your way through CodeLLMs. I hope you enjoyed it. I hope there was a little bit of new information, and it would be great to see you in my next video.